All right, so this is section 10.2, day 2. We're going to continue with the idea of calculus with our parametric curves. Today we're going to start to apply um, things like arc length, and we're actually going to go into some of the um, motion that you can do along a parametric curve. Specifically, we're going to talk about position, velocity, acceleration, and speed when it comes to those. This is probably going to be a 3-video lesson. Um, the first one will probably be the shortest, and then the last two, because the examples take a little bit of time, um, will be the longer ones. Either way, let's get started. All right, so we've learned about arc length when it came to Cartesian or rectangular plane. And the arc length was basically defined by breaking up a curve into very, very, very small linear segments and then adding up all those linear segments. Well, it's really the same idea in parametrics. As a matter of fact, parametrics is probably the easier one to think about because what you have here, we can break this down just a little bit, is underneath of this square root, I have a change of x with respect to t and a change of y with respect to t. So you've got some kind of a change of x, some kind of a change of y, and then we're squaring each one of those two things and adding them together. When you take the square root of that, basically all that is a distance formula. That's literally all that it is. It's finding the hypotenuse of a right triangle, where you've got a change of x, a change of y, so a horizontal change, a vertical change, and then you're going to find the change of the slanted part, which is that square root. And then by integrating from a to b, we're just adding up all of the possible line segments that we get with respect to t. So we're going to make really, really incredibly small line segments, add them all up from a to b. An alternative form of that is the same exact formula. Instead of using dx dt, dy dt, we're going to use f prime of t and g prime of t if you allow f to be, like your x and g to be your y, or vice versa, or whatever. So it's basically the same formula. All right. These can, some of them, be done by hand relatively easily, and relative, of course, is a relative term. Some of them are not going to be so easily done because the algebra and the antiderivative techniques are very difficult. The ones that we're going to do on here, for the most part, we are going to do using a calculator. When you do your web assigns, some of those you will have to try to do by hand because they will only accept exact answers. The answer may end up being pi thirds or something like that, and doing with a calculator you may not recognize that. So some of them can be done by hand using some older antiderivative techniques. Some of them, like the one we're getting ready to do, probably easier just to let the calculator do the work. All right, so we want to calculate the length of the curve defined by the parametric equations. X equals the natural log of t, y equals 1 over t squared. Between the values, t equals 1 and t equals 3. Not extremely incredibly necessary for us to know what this looks like, because they've defined everything for us. They've given us the x and y between t equals 1, t equals 3. So we can just go ahead and use the formula. Again, the formula was the integral from a to b, square root of dx over dt squared plus dy over dt squared dt. So what that tells me is that we need dx dt and we need dy dt. We're given a and b, that's 1 and 3. So let's find dx dt. Well, natural log of t, the derivative of that with respect to t is just 1 over t. And then dy over dt. The derivative of 1 over t squared, again, try not to use the quotient rule. It does work. It's just more tedious and time consuming. Make that t to the negative 2 power. And if you do that, then you would get negative 2t to the negative 3 power. And it's just fine to leave it in that form because in this case, it's going to be easier to plug it in probably to your calculator that way. All right, so let's go ahead and find this. So we're going to have an integral. We'll call this length. We're going to have an integral from 1 to 3 of the square root of 1 over t squared plus negative 2 t to the negative 3 power squared dt. And at this point, I have to assume that you know how to use your calculator to integrate. Again, remember, it's just Math 9. You're probably going to use x's instead of t's, which is perfectly fine, and plug all that stuff in. Assuming you plug it all in correctly, the answer that we get to this problem should be about 1.469. And again, double check that you can plug that stuff into your calculator and get the correct answer. All right, moving on. Number 2, what is the length of the path described by the parametric equations x equals cosine of 3t, y equals sine of t, and t is going to vary from 0 to 2 pi. So once again, what we need is we need the derivatives with respect to t. So the arc length on this one is going to be the integral from, looks like from 0 to 2 pi of the square root. We need the derivative of x with respect to t. A little bit of a chain rule there. That's going to be negative 3 sine of 3t. Again, plugging that into your calculator correctly will be the most important part there. And then plus dy dt, which is going to be the derivative of the y part with respect to t, which is just cosine of t. And we'll square that dt. So parentheses, usage, all that kind of stuff, that's going to be the most important part, plugging the stuff in. And if you plug that in correctly, you should get that the arc length is approximately 13.065. Make that actually look like a decimal. There we go. All right, not much to it if you're allowed to use your calculator. Again, the hardest parts are going to be plugging the stuff in, finding the derivatives. Just don't make any silly mistakes. But other than that, not too difficult. All right, number 3. What is the length of the curve described by the parametric equations x equals ln of t, that whole thing squared, y equals 1/3 of the quantity 3t plus 1 cubed from 1 to 2? Again, same exact idea. We've just got to find the derivatives. These are slightly more involved derivatives, so let's just go ahead and write them out. So dx over dt. Let's see, we'll have a chain rule here, so we've got to bring the 2 out to the front. Natural log of t to the first power times the derivative of the inside, which is 1 over t. So we can kind of rewrite that as 2 ln of t all over t. And then we've got dy over dt, which, again, chain rule, will bring the 3 out front, multiply it by the 1/3. That just becomes 1. So it'll be 3t plus 1 to the second power. And then again, chain rule of the inside times 3. So we should be able to use these now and find the arc length. Arc length will be an integral from 1 to 2 of the square root of my dx dt and dy dt squared added together. So we are going to get 2 ln of t over t, that whole thing squared, plus 3t plus 1 squared, that whole thing squared. Don't leave the 3 out of the parentheses. dt. Then again, plugging this into your calculator, you get 93.001. Very close to 93. All right, that's example number 3. Example number 4, kind of a cool example. Let's see, find the perimeter of the cardioids given by x equals 1 plus cosine t times cosine t, and y equals 1 plus cosine t times sine t. So this word right here, if we haven't already talked about it, whoops, didn't mean to erase that, this word right here, cardioids. It's actually a shape that you can create in parametric and polar coordinates, which we will start talking about in the next section in much more detail. If you're not familiar with them, it's okay. You can plug this stuff into your calculator if you want to kind of see what they look like. We haven't actually done how to plug parametrics and polar into the calculator just yet, but if you know how to do that, go for it. Cardioid is so named because basically the shape has kind of a heart shape to it. It's kind of circular in nature, but then it comes to a point. It kind of looks something like this. That's kind of what cardioids look like, and it can be turned in different ways on the side and so forth. But that's what a cardioid looks like. Anyway, it says to find the perimeter of the cardioid that's given by those parametric equations. Well, to find the perimeter of something, you're finding the outside of it. Normally, if it was just a circle, we would call it the circumference. But the perimeter is just the outside, so it is just the arc length. Now, given the fact that you know now what the cardioid looks like, you're going to have to integrate this in basically what would be in complete circular fashion. So you're going to have to integrate from 0 to 2 pi because basically you've got to cover an entire circle. Again, not something that we've talked about up to this point. We will talk about it much more in detail when we get to the next sections, the polar sections 10.3 and 10.4. But for now, know that to find the perimeter of a cardioid, since it's the outside of it, the circumference basically of it, you're going to have to go from 0 to 2 pi. So we will have to take the arc length. Well, actually, I'm going to put that down here from 0 to 2 pi because these derivatives are not going to be quite so easy. You can do one of two things here, or a couple different things. You can distribute the cosine of t and the sine of t into the parentheses and take the derivative that way, or you can treat this as a basic product rule and do it that way. I'm going to do the product rule method, but you do however you feel is comfortable. Dx over dt. Let's see. So this is going to be my first piece, or my f piece there. So the derivative of that is going to be negative sine t times the second piece, which is cosine t, plus the derivative of cosine t, which is negative sine t, times that first piece, which is 1 plus cosine t. And then dy over dt, very similar. Let's see, the derivative of that first piece is going to be negative sine t times the second piece, which is sine t, plus the derivative of the second piece, which is cosine t, times the first piece, which is 1 plus cosine t. That's a lot to put in here. So we are going to integrate square root of, to leave a lot of space, dt on the end. The first one, all that stuff squared, so that's going to be negative sine t cosine t minus sine t, distributing that, minus sine t cosine t, all that squared. Yes, I am aware that that interior will simplify a little bit, and I'll talk about that in a second. Plus, let's see, we're going to get negative sine t squared, to put this in a bracket here, plus cosine t plus cosine t squared. And I have to square that whole thing. All right, so the reason I said I was going to have to talk about this in a second is because, yes, you can simplify the stuff that's underneath of there, and if you are really good with your trigonometric identities and things like that, this one actually can be done by hand. It takes a little bit. You have to have some knowledge of your identities and be able to use them correctly, but it actually does simplify by hand. And the reason that I would know that is because even when you plug this into your calculator, your answer is 8. Okay, you're not going to get a nice easy number like 8 unless everything on the inside of there simplifies nicely and you get a nice easy antiderivative to take at the end of that. So if you want to really challenge yourself, go ahead and do that one by hand. If not, and I completely understand if you don't, just know that that one could be done by hand, but when you plug it in the calculator, you get 8. All right, that is enough for video number 1. We'll come back with another video and probably a third.